Okay, so next we want to talk about how do you go from this integral equation to a set of matrix equations. Ultimately, we're going to take these integrals, that is the example I just shown here, and put this on a computer. And you can't just jump straight from a continuous integral to a form that's amenable to writing code inside a computer. What's easier, as probably many of you know, is manipulating matrices inside a computer. So you will need to think about, how do you take that step? How do you go from this theoretical integral equation to getting a matrix equation? So we're going to revisit variational methods, talk about how do you get to that point. So there's something called the Ritz method, and what it allows us to do is, what it's focused on is obtaining a suitable set of functions. Recall, we're interested in weight functions that will approximate these finite element solutions. So you have these weight functions, phi sub j. Here are the unknown constants at the nodes, and we substitute that in to some strong form, or actually here's my strong form, is the integrand times the weight functions. So through integration by parts or product rule, you manipulate the derivatives. This changes from solely as an integral equation to having points on the boundary that you have to evaluate. And when thinking about this Ritz method, there's a specific form of this called Galerkin method, where these weight functions, I've defined it as w sub I, because its notation of a subscript will be clarified later, but it depends on how many finite elements you have in your system of equations. So in Galerkin's method, the weight function is the same as this interpolation function. They don't necessarily have to be, okay? There are some subtleties between those. Basically, we'll get into this again in more depth later, but this weight function here and what we use to approximate the solution don't have to be the same. We make them the same when we use Galerkin's method. So the solution of our dependent variable u is approximated by phi sub j, these constants, and the weight function w is also approximated by the same type function. So you notice here's phi sub I, this is what used to be w, and we have this summation is the approximation of our dependent variable u. And then you bring down w, f as some type of body force, and then here is my boundary conditions. So everything's in terms of these polynomial, what we'll use as polynomial functions. Okay? So this gets closer to what we're interested in terms of a set of matrix equations. So you need to think about, how do I go from this summation and these indices I to a matrix equation, right? So this form here is equivalent to this matrix equation. So this is a matrix. It has rows and columns. This is a column vector C. These are my unknown constants here. And then I have a vector for boundary conditions Q, and here is my internal force F. So these have been discretized at every node in the finite element problem. More specifically, here is K, here is F, and here is Q. Alright, so let's talk about this in terms of an example. So I've got a rod, properties, thermal conductivity. This is a believe this is a convection coefficient. So this is very similar to the other problem we talked about before, except there's no heat generation. So I'm going to use a 2-parameter Ritz approximation, and I'm going to use polynomials for the weight function and the approximation function of the solution. So here is our ODE that defines how this rod behaves under a thermal gradient. And we've defined theta as a delta T, so the temperature minus the ambient temperature. I also introduced this parameter C. It's a function of the convection coefficient, cross-section area, conductivity, and the perimeter of the rod. My boundary conditions. So on one side it's 100 degrees C. So you note here just the delta T. And then on the other end I have this boundary condition. So this is insulating on the other side. Alright, so we take the weak form. We've already went through integration by parts. I'm showing the final weak form where we have to evaluate this integral, and here are my boundary conditions, right? So you do have to be careful in how you define this on this side. So remember, we have this definition, okay? So this is a balance of internal thermal conductivity and convection is 0. So in the weak form you have this at the endpoint. So that means k d theta dx is equal to minus beta times theta based on this. So we can do a substitution into here. Okay. For the weighted residual method, it turns out that phi naught is going to be a 100 to make sure we satisfy boundary conditions on the left side, where x equals 0. And then if we define phi as being linear as a function of x, we have this relation, right? Given this definition, this is automatically satisfied as x equals 0. Alright, so after substituting in the boundary conditions, we have this on the far right at x equals L. Here's my integrand that I have to approximate. So I take this, how we define theta, as an approximation of these interpolation functions as well as phi naught. And here's my Galerkin formulation. And I'm going to introduce this parameter c hat as just beta over k. Alright, so substituting these in from here, I get this form of the equation. And again, we have this for phi naught, this is 100. And letting this be our function here. Keep in mind, this is a guess, so this is one type function we could use to solve this problem. We'll get into later how we can use different types of functions, but this is just one that happens to work for this problem. So we introduce this notation. So if you look in Reddy's book, page 75, he uses bilinear type formulation. It basically means that you have a matrix of this form, where here is my Bij. It includes the integral, includes this boundary condition, and then he defines f in terms of this component of the integrand. It only has phi naught, and then this term. So using units of meters, we have a length. We have, if you go through, and I recommend you go through and evaluate these integrals, you'll find that we have these coefficients. And we also have f1 and f2. So ultimately, here's what we get. So these are known, now you can invert and get these two constants. Once you have these two constants, you have this Ritz approximation. Okay, so now you know the temperature everywhere in the bar using this type of approximation.